Good morning, everyone. Welcome to our QuakeCoRE seminar for the month of August. And today we're going to discuss a very important topic for New Zealand, the topic of building retrofit. And we're lucky enough to have with us Alex Shegay and Ken Elwood, who are going to share with us lessons they learned in a reconnaissance mission they did in Taiwan earlier this year, where they were able to observe the benefits of retrofit that was done there to improve the performance of buildings, mostly reinforced concrete buildings. Alex is a lecturer at the University of Auckland, where he also got his Ph.D. And Ken Elwood is, of course, Professor of Engineering and also at University of Auckland, and he acts right now as Chief Engineer for the Ministry of Business, Innovation and Employment. So I'd like to thank them both for sharing their time with us, and I look forward to what they have in store to tell us.
So my name is Alex Shegay. I'm a lecturer at the University of Auckland. I'm presenting today on a reconnaissance we undertook in Taiwan in Hualien City. With me presenting will be Ken Elwood, who I'm sure most of you know. And yeah, I guess we'll kick things off, and I think we've got about 25 minutes of presentations and then about 15 minutes of questions. So I'm going to jump straight into the earthquake details, and then I'll kind of leave the background of why we went to this earthquake to present a few slides later. I'm getting my pointer out. Okay. So first of all, just some acknowledgements right from the start. So these are a few organizations and people to acknowledge. Of course, QuakeCoRE, Natural Hazards Commission, INCRE, Catalyst, Seeding Fund, and might seem strange, but JSPS, the Japanese Society for the Promotion of Science, also helped fund this trip. So I'll get into how they were involved a bit later. Also, thanks to Professor Shijiang Huang and Hangjin Li and Seung-Chin Cho of INCRE, who helped provide some of the content for this presentation. So today, I'll talk about the background of the earthquake, why we undertook it, and some of the damage observations from our trip. And then I'll pass over to Ken to talk about some findings we had about retrofit policy and performance of retrofit buildings. So I always like to start with a map. I'm sure most of you know where Taiwan is, but it's always good to get orientated. So Taiwan's located just off the coast of China here, about a 10, 11-ish hour flight from New Zealand. So I didn't know this until I started looking into this, but Taiwan actually sits on the Philippine Sea Plate, on the corner of the Philippine Sea Plate, which is quite interesting because it has movements from, I guess, all directions coming into it. It sits on the corner with the Eurasian plate, and this is an image I found. You can see it's a very old image, but I don't think things have moved too much. Should still be accurate, but basically, because it sits on a corner, you've got the Philippine sea plate subducting on the northern end and rising over the Eurasian plates on the western end. And most of the earthquakes actually occur in this subduction zone, which is the Ryukyu Trench, but a lot of these earthquakes are off the coast and are not very damaging. The more rare ones that happen where this Philippine plate rides on top of the Eurasian plate is what causes the most damaging earthquakes that we've or they have seen in history. So this is a quick overview of previous earthquakes, I guess the recent ones at least. The most well-known, I guess, would be the 1999 Chichi earthquake, but since then, every few years, I guess, they've had another earthquake with very similar looking damage. This is the one we're going to be talking about today. But in the corner here, I've written a couple of more years which correspond to some of the biggest earthquakes in Taiwan, which resulted in the most amount of damage and the most amount of casualties. And you can see that between these three, 1999, it seems that quite a significant earthquake happens in Taiwan on average every 30 years. When I kind of saw this history, it made me think of if Hualien was, that once in a 30-year earthquake that seems to happen, that's causing a lot of damage. On the bottom here, I won't talk too much about this, but is a history of how the design standard has evolved in Taiwan. Significant changes happened in 1997, 2005, and we're in 2011. You'll see that the buildings that we looked at in Hualien were mostly pre-2000s, so before some of these new provisions about consideration of MC earthquakes and consideration of local side effects came into practice. Down here is some information about how the retrofit programs have evolved over the years, but I'll leave some of that detail to Ken to discuss. So the earthquake overview on the left is the 0.3 second spectral acceleration graph. In the middle is damaged buildings in Taipei at the top and Hualien City at the bottom. So the earthquake happened on the 3rd of April in 2024 at a depth of about 40 km, about 15 kilometers south of Hualien City. So there's Hualien City, and the epicenter was where this red cross is, but actually it got moved closer to the coast after some revisions, and quite a while away from Taipei City. In total, there's about 28 buildings that had partial or total collapse, but through all that, only one person actually lost their life as a result of this earthquake. And even then, I think that person escaped from the building during the first earthquake and then ran back in to save their cat and died in the collapse of that building in the aftershock, which came, I think, about 15 minutes later. And there's some similarities with how this earthquake looks to the Darfield earthquake in 2010. So similar distances from the city, similar depths, and similar fatalities. But what's interesting is even 150 kilometers away, there was damage in Taipei, which is all the way up here, despite the earthquake being so far away. The biggest accelerations were felt in the mountains, actually, with Hualien feeling a little bit less than the mountains. I'm better speed up here. So these are some of the spectral acceleration plots around the city. The very first one we saw was this one in the middle, which had high accelerations before the 1 second period mark. The red and purple line correspond to design based on MCE earthquake spectras. So you can see that shaking was very high. But as we started to discover other spectras in the area, we saw that in some cases, the spectral accelerations above the 1 second mark were also very much above MCE level earthquakes. So why did we decide to go and view, do a reconnaissance of Hualien despite not seeing that many fatalities or damage? Well, we know there's ongoing efforts in New Zealand in developing retrofit guidance, and we also knew that a lot of retrofitted buildings in Taiwan performed really well. So that was a really good case study for us to go and understand what they have been doing that seems to be so successful. And on top of that, myself and Tomomi Suzuki, which is pictured up over here, we have an existing project from the Royal Society of New Zealand, the Catalyst Seeding Project, on looking into cost-effective retrofits. So all these three things came together at the same time, and we put together a team from New Zealand, from Japan, and from Taiwan, led by Jason, to undertake this reconnaissance, with the main objective being to investigate the policy behind implementation and the performance of retrofits using simple techniques. We'll talk about what simple means a little bit later. So the building stock overview in Taiwan consists, in Hualien consists of, corner buildings are notorious for being, vulnerable to these earthquakes. row buildings, so similar low to mid-story height buildings lined up, abutting, and multi-story apartment buildings as well. So the ones that we looked at, a summary is shown in the plots that follow. Most of them were residential, with the next biggest use being commercial. But to be honest, a lot of these buildings have a mixed use, so they might have a shop at the bottom with some residential floors up the top. So this is just showing the predominant use. This graph shows the placard given to the building versus how many stories it had. And you can see, despite quite high accelerations at low period range, quite a lot of buildings low to mid story perform quite well, with a lot of these red buildings having some sort of construction deficiency or construction error. The surprise, I guess, for us was a lot of these high-rise structures didn't seem to be performing so well. In terms of the year, you can see that most of these buildings are before the 1997 code came into place, and before the 2005 code came into place, which is when MCE checks and consideration for local side effects came into play. So at first, when you look at the damaged building, so each pin corresponds to either a red tag or a yellow tag, with the dark red showing demolished buildings. It looks quite severe, but when you plot all the other buildings that we looked at onto the graph, onto the map, it actually doesn't look so bad. So the damage was quite dispersed and actually overall quite limited. And there was a bit of a mystery for us, considering that spike we saw at below the 1 second period mark in the spectral accelerations. But when we started to look at some of the other spectral acceleration records in the area, we saw that actually a lot of the areas had reduced demands at the low small period ranges and a peak at 1+ second ranges. So just a quick overview of the damage that we observed for low-rise structures. Here's a corner building. Typically, we often saw hinging in the columns, so it's, I guess, a soft story collapse, which has quite been repetitively seen in Taiwan over the past few years in earthquakes. But it's often accompanied with images like this, where you see either a splice in the plastic hinge under the column, and even when you do have a splice, it's quite poorly detailed. So you can see these quite a significant lack of transverse reinforcement. In other cases, the structure had low reinforcement ratio and high axial demands, such as this one here. One other contributing factor is often that these buildings had an asymmetrical placement of vertical elements. So particularly the corner buildings, this is a plan of this building specifically, you'd often have a structural wall or an infill wall along the back face with some non-structural partitions, which results in a lot of stiffness on the back face and not much stiffness on the street front. And so the torsional response contributes significantly to the damage that we have seen. Of course, yeah, like I said, poor detailing in a lot of these buildings contributed to some of the damage that we saw. For high-rise residential, this is one case study that I'll show, which has 3 buildings on a common podium, with the peripheral buildings experiencing severe damage, with the central building experiencing moderate damage. So trying to figure out why the difference happened despite these buildings being so close to each other. Again, like I said, there's that peak above the 1 second mark in the spectral acceleration plot, well above the MCE spectra, which eventually helped us explain why these high-rise buildings were experiencing the damage that we saw. So looking at these peripheral buildings first, you basically had double height columns on the outside here, but single height columns on the inside, which essentially resulted in deformation, incompatibility, and eventual failure of these internal columns. In addition, although there were some walls present on the inside in the longitudinal direction, it wasn't quite clear if these were structural walls. So they were quite thick. I think they were about 250 or 300 millimeters thick, but the reinforcement didn't seem to correspond to that, very lightly reinforced. And so you had quite severe axial failures and through the thickness, axial failures in the walls as well. In the transverse direction, you can see the spans are very large and there's no walls to take up some of the lateral demands. And so this is part of the reason we think this building experienced the damage that we saw. Of course, it didn't help when you have fire hydrants running through your concrete sections as well. In comparison, the central building, which had moderate damage, you can see each one of these blue, yellow, orange boxes corresponds to one of these pictures. Although some of the pictures, some of the damage looked quite severe, such as this picture here, these turned out to be non-structural walls, so like 100 millimeter thick walls with single layer reinforcing. So they would not be considered as severe structural failure, whereas some of the structural walls, which this building did have, didn't have as much damage. Some light cracking was observed. You can see that the frame in general, this is a picture looking down the hall here, is looking quite healthy overall. Of course, there was, again, some construction issues. You can see here is a lap splice and the column hinge when all the transverse reinforcement is lumped to the top. So I guess your transverse reinforcement ratio is correct, but not well distributed. And really bizarre cases of concrete cores being taken out of a column, but then getting put back in for whatever reason. So that got exposed during the earthquake too. So unlike the other one, this one seems potentially repairable, whereas I think the local government was saying both can be repaired. And this is a list of common construction errors that we observed, or in case of partition walls, maybe oversights. So these internal partition walls are not designed to be structural, but they're made of concrete or infill masonry. And so they will act as a structural component, which can drive your shear demands into the columns, causing some of the damage we observed. You know, there's issues like this where that's just a construction issue where the contractor couldn't get the hoops around the couplers, so they put the hoops inside the longitudinal reinforcement, so that didn't help. Concrete cover in columns being cumulatively thicker than the column itself, and then some PVC reinforcement running through the center of the column. So in terms of the actual quantitative data that we collected, something called the Hassan index, which some of you might have heard of, is basically two indices, and it's an area ratio. It's an area ratio of the area of walls over the area of the entire floor plan, and the area of columns over the area of the entire floor plan. And so a simple way to think about this is the numerator is your capacity, and the denominator is your demand. So how much, I guess, inertial mass you have on your floor. And numerous studies in the past have studied how these indices relate to damage. And in general, if you plot the wall index and the column index on the X and Y axis, you can think of it as like a 2D capacity to demand ratio. Then anything in the corner which has not many walls and not many columns should experience severe damage. Anything towards the right-hand corner will have a healthy building. And so data from earthquakes seems to support that in general. Here is data from Taiwan in 2016. This is from, I think, a Turkish earthquake in the 30s. So we did the same thing with the buildings that we looked at. We classified them in, I guess, low damage and high damage, which is the orange and the blue. And generally, the data seem to agree with this red boundary that's been proposed by Hassan, which is supposed to divide your damaged to undamaged buildings. This plot, of course, doesn't take into account any account for the size of the demand. So you expect it to have some blues go under the line and maybe some orange even go over the line. Of course, it's a very crude index. Things like construction errors are not captured. But one prevalent issue in Taiwan is this issue of having torsional irregularities. So now we're thinking about how we can penalize some of these points for the fact that they have torsional irregularity in the plan. Another use of this map is potentially to use it to identify critical buildings in the city that hasn't been struck by an earthquake, to then say, well, if your building is placed over here, perhaps this will be a priority for retrofit. So Taiwan did do this in one of their retrofit programs. They used this method to identify, I guess, critical cases. Here is some data of us demonstrating how that may work. This is a building we looked at, E35, which had no retrofit. And this is the building E36, which did have retrofit. They're very similar buildings, very similar location. But the E35 has low low column ratio. And then for E36, they ejected the columns, put some walls in, and drove this point outside the red line. And so the impact of that is that this building had axial failures in the columns, whereas this building looked a lot healthier. So this is one way with how we can use one of these plots to, I guess, prioritize retrofits. I'll pass over to Ken here to continue talking about retrofit in Japan.
All right, thanks, Alex. Let me just share my screen. Trust you can all see that now. All right, thanks. Great to talk to people at QuakeCoRE again. I was pleased to be able to join this reconnaissance with Alex and the team, and Tomomi and the Japanese team, as I've done a fair bit of work in Taiwan in the past. NCRE is one of QuakeCoRE's international affiliate organizations. And they've instigated several different retrofit policies over the last several years, starting from the time of the Chichi earthquake in 1999. So this is the same slide that Alex showed earlier. I'm going to talk about these two programs in orange at the bottom here. First, the school retrofit program, and then the private building retrofit program, and then give you some reflections I've had in relation to how those might play out, or what I took away from this in terms of lessons for New Zealand. We're running a bit behind time, so I may skip through some of these a bit quickly. So the school retrofitting program in Taiwan was initiated shortly after the Chichi earthquake, where there were several hundred severely damaged and some collapsed schools out of the Chichi earthquake. What I particularly want QuakeCoRE people to notice here is that they specifically ran a 10-year program to prepare for the execution of this retrofit program. And in that time, NCRE did a very significant research program on the performance of school buildings, really trying to refine their ability to assess these buildings and develop cost-effective retrofits. And then after that preparation, after that research and the development of guidelines, then the execution of the retrofit program was initiated in 2009. And it's been running now for over 14 years. The latest numbers we have in terms of the total retrofits are from a couple of years ago, but they're about 37% of the way through. They're all indications is that it's been really quite effective. So buildings that are subject to this program are essentially all buildings constructed prior to the Chichi earthquake that are occupied by people. The retrofit requirement is they must be upgraded to 100% of the 2011 building code. If there are any other future changes to the building code, that does not affect the target that they're retrofitted to. They continue to use that 2011 code as their benchmark. As part of that research that I referred to, they actually tested some schools. And so this is a video of one of those tests where they actually pushed the school over or the building over to really test what is the collapse capacity of the building. By doing that, they were able to make the assessments much more accurate, really sharpen that pencil to be able to identify the worst of the worst buildings for retrofit and make those retrofits more cost effective. It's very impressive. They've managed to keep those retrofit costs to about 11% of the rebuild cost of the school. That's remarkable, considering the costs we're seeing here in New Zealand for retrofit. So one example of a school that we visited in Hualien was the Hualien Girls High School. And there are essentially two buildings right next to each other. One that was not retrofitted, that was very severely damaged, probably close to collapse. The other retrofitted one, almost not a scratch on it. So showing the advantage of having retrofitted that building, obviously. But what's interesting is that non-retrofitted building in red there, in the red box, was assessed by a very early assessment methodology that they put in place in the program. And that assessment methodology showed it was okay. And that's why it was not retrofitted. When subject to a more updated assessment methodology, they actually found that it was not okay and it should have been retrofitted. And that just points to the importance of us keeping our assessment methodologies up to date, because we do learn things over time and need to implement those learnings. The private building retrofit program is quite a bit more complex, as private buildings are obviously owned by all different people. You don't have a single ministry to work with and so on. It is a voluntary program in Taiwan. They're really focused on the concrete buildings, particularly those with soft and weak first stories that have been observed to fail again and again in past earthquakes. They essentially give two options here. Either you do just a weak story retrofit, you just fix that prominent vulnerability, or you can retrofit up to 80% of that 2011 code. There's a subsidy given for this. And there's a limit on that subsidy, and that amount is actually pretty modest, right? I mean, when you think about retrofit costs these days, that's not a huge amount there, up to a maximum of 230,000, and that really puts pressure on the engineer, on the building owner, to try to keep those costs down as much as possible, to get as much bang for buck as possible. There's some discomfort among the engineering community of doing weak story only retrofits, where you only focus on that one vulnerability for the retrofit. There's a feeling that in order to get that to roll out more widely across Taiwan, there's going to be a need to develop some legislation to protect engineers using that form of retrofit. That's still in progress, but it has been implemented in several cases. Here is a building in Hualien that had a weak story failure, and in the background you can see a building that was retrofitted with BRBs, primarily first story. There are actually BRBs extending up here, but it was primarily that weak story retrofit. And I tend to call this your biggest bang for buck retrofit. If you sort of plot the risk reduction that you get against the cost of the retrofit that's needed to address that vulnerability, this is your biggest bang for buck retrofit. And in the case of Taiwan buildings, it's relatively obvious what this big bang for buck is. It is this weak story, and predominantly the weak ground story. In New Zealand, as I'll talk about in a moment, it's not always quite so obvious. A few examples where this was these retrofits were applied to private buildings in Hualien, where essentially really good performance of all these cases. And you can see those retrofit costs at the bottom, really reasonable costs. And you can see how the weak story retrofit is considerably cheaper than that 80% of code. Now, the overall construction costs of new buildings in Taiwan is probably about 25% of what we see here in New Zealand. So you could maybe multiply these by a factor of 4 to sort of do a translation to our construction environment for what these real numbers would be. But those are still very, very reasonable costs. So as I said, I wanted to sort of think about this in a New Zealand context. And I think probably the closest analogy is really the unreinforced masonry simple strengthening project that is being promoted or being developed by the Joint Committee for Seismic Assessment and Retrofit currently. Essentially, the similar concept in that there are simple retrofits focused on the highest risk vulnerabilities. This approach is being applied or considered to be applied on 1 or 2 story unreinforced masonry buildings on sort of Main Street, New Zealand. And the idea is that we'd like to reduce the cost of the retrofits, make them simple, off-the-shelf type of implementation. This is still a project in development, but it really has quite a few similarities to the weak story retrofit approach in Taiwan. In the case of concrete buildings, I think the situation in New Zealand is a bit more complex, and it's harder to establish that single biggest bang for buck retrofit. We've got precast floor issues, we've got non-ductile walls, we've got connections between the diaphragms and the cores, we've got multiple weak story issues. So it's not always obvious where that biggest bang for buck is going to come from. Started thinking about, well, despite that, is there some way in which we could implement something like this in New Zealand? And here I'm going to skip over this slide for a moment, just go straight to the steps. So the first step would be to identify your key building vulnerabilities. And for each of those vulnerabilities, assess a risk as low to very high. And then develop simply a retrofit concept, not a full retrofit design, but just to think about what sort of concept would be used to address each of those vulnerabilities. And then think about what sort of risk reduction are you likely to get from each of those retrofit features that are addressing each of those vulnerabilities. Then, if we had some research that could give us an indication of a cost coefficient for each of those features, and in other words, in a relative sense, how much more expensive or less expensive is its specific retrofit feature relative to another, then maybe we could sort these retrofit features by the risk reduction achieved per cost. And in that way, we could identify what our biggest bang for buck retrofit is and focus in on that. And maybe we could say that bang for buck retrofit might get me below some minimum risk level that I want to achieve, but I can even still plan for reducing that further over time by addressing other vulnerabilities. This is just a concept. It needs further work in a couple of fronts, but something I wanted to share with you as an idea developing amongst the team as we were over there. The other really big thing is they really focus on cost effectiveness. And a good example of that is their approach to the foundations that are put under some of the retrofits. So, for example, if you have a simple frame here and you say you want to put a concrete wall in to retrofit it, here in New Zealand, we'd likely also accompany that with a pretty significant foundation for that new wall. And in Taiwan, they say, no, the wall's going to make it better, so let's just leave it at that. And it's I have a huge savings by not putting in a new foundation. So, and we probably accept that easily. For 4 stories, maybe accept that as well. There's probably a limit, however, where when you start to get much taller, then you're probably going to want to have some form of new foundation put in as well. So again, I think there's some research needed here to identify what that limit might be. So with that, I'm afraid we've gone a little bit over, but let me just summarize a few key messages from Alex and myself. There has been investment in building code improvements over the years, and particularly since the 1999 Chichi earthquake. And we see that paying off in terms of lower losses and faster recovery in these more recent earthquakes. The simple area indices that Alex talked about look like they can be useful for triaging structures for retrofit. The approach in Taiwan of focusing on simple, cost-effective retrofits we see as an effective way of achieving wider implementation. It's interesting, in New Zealand, they take a different approach for their private buildings. They use subsidies with voluntary programs, as opposed to here in New Zealand, we have a mandatory program without subsidy. So I think it's good to see these differences of approaches. And whenever we see those differences of approaches, there's great opportunities to learn. With that, I think we open it up in the last 5 minutes here for some questions.
Thank you, Ken, and thank you, Alex. I think what you presented here is very informative, very useful. So again, I'd like to thank you. This is such an urgent topic for us, and the effort to go to Taiwan and bring these lessons is much appreciated.